Okay. So here we have a thin hoop of uniform positive charge. And we want to calculate the electric field strength at point P. And I'll tell you right now, in this class, this axis is the only place that we'd actually be able to calculate the electric field strength on. Maybe on the Y and Z axis too, but actually be a little more complicated than that in those cases than it would be for here. Note that this is three-dimensional. This is in 3 dimensions. I've tried to draw it as such, so this is a ring that is oriented like this with the axis, x-axis pointing to the right. I've just offset it a little bit so that I can diagram some stuff on there. Because we're going to follow the same procedures, but it's going to be a little more complex this time. I keep hitting admit, but then it's not letting him in.
It's just a hacker. He must have hacked the
Maybe I need to... Man. That's how you hack, you just type real fast.
Yeah,
You can get anything done.
like flintlock.
You guys ever, do anyone know Red Letter Media? Best YouTube channel. Best YouTube channel. Red Letter Media. They review movies. And there's one where it's a stupid movie where they hacked the plane. And they called it before. And then they're like figuring out how to take control of the plane. They're like, they're going to hack the plane. They're going to hack the plane. And then it looks over at a joystick that's like a flight simulator joystick. And Red Letter Media, recommend it. There's foul language though, so Gianni, you're not allowed to.
Just Johnny,
Okay.
because he's like
If anyone's communicating with Timothy, tell him I've hit admit, but nothing's happening.
He hasn't hit accept admission.
No, he requested admission.
Yeah, but it's still accept.
Okay.
I'll make sure to let you know you kids know the class.
So we're gonna figure out the electric field due to this thin hoop. Thin meaning it's a 3-dimensional. Dimensions don't really matter. We just consider it to be a line of charge that's curved into a hoop. And we want to know the electric field strength here. So as usual, I diagram the situation. I draw a little representative DQ. What we're gonna have to be careful with in this particular case, we're gonna have 2 angles that we're gonna have to deal with. We're going to have to specify DQ in terms of its angle, its angular position on the ring, right? Like from this, like angular position that way. But then there's also going to be an angle for the electric field vector at point P, right?
His computer's being weird, so he's restarting it.
What's that?
Timothy's computer's being weird, so he's
Okay,
restarting it.
okay.
Do you hack his computer?
I am recording this, so I'll be able to see that. Okay, now I have offset DQ down a little bit. Diagramming this is rather difficult, so just bear with me. First of all, we know that this DQ is going to create an electric field at point P that points this way. We'll assume it's a positive charge. That is the electric field DE. We can come to the conclusion, let me extend the x-axis a little bit. We should be able to conclude based on the symmetry of the situation that the electric field in one direction, actually in 2 directions, is going to be 0.
He's trying again.
There it is. So we should be able to see the symmetry here, like the electric field is really going to only point in what direction?
Why?
In Y direction?
Oh, wait.
The X direction.
The X direction, right? It's only going to point in the X direction. Because if you notice, essentially the electric field vectors due to the DQs are going to sweep out a cone, right?
Yeah.
They're going to sweep out a cone, and so all of the electric field vectors that point in the Y and the Z directions, they're all going to cancel out, leaving us just with an electric field in the X direction. So the net electric field is just in the X direction. So I will have to label some angles here. So I got this angle, theta, which is congruent to this angle, because those are what type of angle?
The same.
Well, man,
Vertical.
Yeah, man. The complementary is like
90 degrees.
60 and 30.
Yeah. Silly. Okay. Not only that, though, I have to. Let's see how it's hard to draw this. I have to specify the location of dq in a way that will allow me to write the charge distribution in terms of this circular charge here. And so the only way to really do that is to talk about the position in the zy plane, right? All of the dq's reside in the plane, in the zy plane, or the yz plane. They're not in the plane in the x dimension, right? Just at one location at the origin in the x direction, but they all reside in the zy plane, yz plane. And so I want to specify the angle that this guy makes within that plane. So right there, if I start from the positive z direction, this angle right here, I can specify dq's position in that plane using that angle. And that angle I'll call phi, which is just a circle with the line, vertical line through. Kind of like theta, but the line goes all the way through. And so can you see that? That's like, I'm specifying, remember we have to specify the location of dq every time we do this. So I'm specifying the location of that dq by just measuring this angle. Does that make sense? You got me? You got me? Okay.
do it one more time.
That's all you get. So that's the angle phi. If that's the angle phi, and notice we got a radius, obviously. The radius of our hoop, I'll call big R. If that's the radius of this hoop, this is an arc length. The arc length on which dq resides is just r times d theta. On the macro, r times delta theta, right? Theta, phi.
Yeah.
Delta phi, but delta phi, once it becomes infinitesimally small, it's d phi. Right. And so this is just arc length, right? S equals r theta. Arc length here, r d phi. All right?
This will be RD feet.
Feet.
Funny.
Now, what do I call this distance in our equation that we've always done?
Little r?
Little r. That's why I call this guy big R, because I have the little r here too, right? Which, if you haven't noticed yet, this is a little more involved than what we've done before. And let me go ahead and, this is R. The length, the distance from the charge to the point at which we're trying to calculate the field. That's R. This distance right here is x, right? That's just the position in the x direction of the point in question. Might be useful in the future. Right? I'm just labeling everything that might end up being useful. And I said at the beginning, but I didn't say it on the video. We're going to use the result from this one to determine what the electric field at point P would be if this was actually a sheet of charge, a circular sheet of charge. And then we'll take the limit as the dimensions of that sheet approach infinitely large, an infinitely extent, a charged sheet of infinite extent in the YZ plane, finding the electric field here. That's the electric field that's generated by one single capacitor plate. And so it's going to be the essence of the electric field strength in capacitors. So the result is very important, one that you'll commit to memory, and is actually a pretty simple, small expression that will have a lot of stuff leading to it.
I'm showing this diagram to like a kid in kindergarten.
This is what you're gonna learn in like 12 years.
I'm sure they wouldn't even, they'd be like, yeah, whatever. Let me go back to picking my nose.
Well, obviously, if you do this and this, you'll calculate the electric field of ease.
Okay, so some things to notice. By symmetry, the electric field, the total electric field is simply the electric field in the x direction, right? So all I need to worry about is dE in the x direction. As always, this is a line of charge. This is a line of charge So it's going to be lambda. It's going to be total charge divided by the length, but because this is a hoop, that's going to be charge divided by 2 pi times big R. Again, the macro charge density we usually use to simplify our result at the end. But we also know that it's simply the charge per unit length for dq. So dq over that length, which is r d feet. And that's what we use to substitute, to change our dq into something that we can integrate with respect to. Notice that means we're going to be integrating with respect to what variable? Feet. Not theta. Why not theta?
Theta is constant.
Theta's good. Yeah, good. That's like the opposite of stupid. That was very good.
Yeah.
You're fired. Theta doesn't change here. Theta doesn't change, right? Remember, this makes a cone about the x-axis, and theta is going to be the same for all DQs, all electric fields generated by DQ, no matter what Mr. Henderson tries to tell you.
Yeah.
Cones are stupid, so.
However, theta does change, right? As I integrate over the hoop. Phi does change as I integrate over the hoop, right? Yes. Oh my gosh. I wish it was Friday.
Yeah, me too.
So I know I'm going to make that substitution. dq is going to be lambda times the radius times d phi, not d theta. Man, I'm betting 1,000. Okay. So again, we are integrating with respect to phi because that is the only thing that changes here. X doesn't change, theta doesn't change, r doesn't change, none of that stuff changes. The only thing that changes is going to be phi. And so that's what we integrate with respect to, and that's what our charge density equation tells us. Okay. So we already started, but we write an equation for this, the simple equation for electric field strength, right? The one that's not too difficult. We do have to add the cosine component though. dE in the x direction is going to be k times dq over r squared. But it's the x component of that, so it's going to be times the cosine of the angle theta. That one's theta. Are you trying to trip me up? That one's theta. This component, this is
I
the...
got you. Okay, yes.
You're not messing with me, are you?
That's for you to decide.
Okay.
Understood.
Now, okay. So typically in this type of a problem, and to lead to the conclusion that we want, that we won't get to today, it'll probably be Tuesday that we'll get to it. To lead to that conclusion, what we want to do is express R in terms of the physical quantities described by our situation. So we have a point that's an x direction, x distance away from the origin, and then we have our dimensions of the hoop here. So I don't actually want R. I want to express R in terms of the dimensions of my oh my gosh, it's Friday, right? Please tell me it's Friday. Good. I want to express R in terms of the dimensions of the hoop and the distance to the point. All I'm trying to say is I want to use the Pythagorean theorem to express R as something different. Okay. So like we did the other day, we had to do it the other day though because R actually changed, and so we had to express it in terms of the variable that changed. We don't technically have to do that here, but to get to the conclusion that we're going to reach eventually on Tuesday, we want to express R in terms of X and what other variable, or what other symbol, what other quantity. We're actually going to want to do the same thing with cosine theta too.
Okay, so
X and which R?
Little.
big R.
Big R.
Yeah, that, yeah.
The right triangle with little r and big, like you have a right triangle there.
And then just, yeah.
No matter where DQ is, right? Yeah, but if you think of it as a cone, but this distance, think of if DQ is way up here, this distance is big R, this distance is R, that distance is X.
Yeah,
So I am not explaining this well, I apologize. My bad.
R
I'll blame Sullivan.
That makes
plus the
sense.
square root of r squared plus x squared.
Which are both constant, so technically we don't need to do this.
Oh. If you would have just said do the Pythagorean theorem, I mean, that would have been a whole bunch
Yeah, my bad. Sorry. Now that being the case, I can express cosine of theta as what?
X over big R.
X over,
Yeah,
x over
yeah.
little r.
X over little r, which I have this. Right, cosine of this angle, this side, divided by the hypotenuse.
Yes.
I'll blame Timothy for that since he's not here.
Oh yeah, how dare you, Timothy?
It's all your fault, Timothy. Okay, and so I can make those substitutions into this equation. dE in the x direction equals k. Substitute my lambda r d phi. Lambda r d phi. Divided by r squared. What's r squared?
R squared
Big R
plus x
squared
squared.
plus X
Big R squared plus x squared times the cosine of the angle. So times x over the square root. Now I'm going to write it like this because this happens a lot in these types of integrals. Very often it's more convenient to write radicals as exponents. And be careful because when you multiply that, you got to have this guy raised to the 1 power, right? You're not just distributing that x squared over those two things. It's that quantity times that quantity. Which I can simplify. Which looks gross, but as you'll see, the calculus in this problem is very easy. Very easy. So I have k, I can bring the x out, kx lambda r d phi over, well that equals, over, and what do I get in the denominator?
R squared plus big R squared plus x squared to the 3 halves.
To the 3 halves power. Okay. And then I need to integrate both sides, right?
Yes, sir.
When I integrate the total electric field in the x direction, I get the total electric field.
Wait, so is it just the integral of dp?
Yeah,
Wait, yeah, I literally.
yeah. Everything else is constant. So what are my limits, though?
From 0 to x.
We're integrating from 0 to here. We're integrating
No.
phi from 0 to here.
No.
From
0 to 2 pi.
Yeah, exactly.
We want to go all the way around the hoop, right? So our limits of integration are going to be from 0 to 2 pi. And all the constants come out, which are k and x and lambda and r. And the denominator constants come out, which are r squared plus x squared to the 3 halves times the integral from 0 to 2 pi of dv. And this is a central theme to a lot of the calculus we do in this class, even when we get to Maxwell's equations. I told you that when I put those crazy looking equations up, but then I told you the integrals are very often the easy part. In this situation, it's definitely the easy part. The integral is the easiest part of this problem. Right? What's the integral of d phi?
I don't know.
1/2 e squared.
I'm pretty sure this is the one we gotta look up in the book, right?
Yeah, you gotta look up a table to get this one. What's the integral of d phi? Phi. Evaluate it from 0 to 2 pi. Which means I can just put 2 pi in for phi, right? Right?
Yeah.
So the electric field is going to be 2 pi x r. I'm going to plug in the expression for the charge density over r squared plus x squared to the 3 halves times, and I'm going to plug in for lambda q over 2 pi r. Notice that things simplify whenever we plug in the charge density, right?
2 pi r.
2 pi r cancels out.
So it's x cubed over r squared plus x squared to the 3 halves.
It's going to be q times x over r squared plus x squared to the 3 halves. Right?
Yes.
Did I miss anything?
No.
I did miss. Oh, yeah. No, yeah, we're good. We're good. Yeah. Sorry. I was thinking about the dimensions again, but the dimensions work out. K. There's K. I see. I knew something was wrong. I was testing you guys, and you failed miserably.
No, I was looking at this.
Joel whispered it to me.
Did you really? And if I wanted to be specific, I'd say the electric field vector is this quantity, this magnitude, times the I hat direction, and it's positive in that direction. All right.
Could you simplify the bottom to r cubed plus x cubed?
Yes, but why would you want to do that?
No.
Just kind of.
No, it's because it's a square root of a binomial that's both.
Yeah.
You have to complete the square.
Yeah, obviously.
Obviously.
Now it's just another test.
Who were you testing?
Mr.
Graham.
Graham. Obviously. Pop quiz.
Though I don't remember how to complete the square.
Well, then you failed.
All right, so we might actually have time to do this. So I'm going to write this result up here. The electric field is equal to k q x, because we're actually going to use this result. R squared plus x squared. The 3 halves times I. So let's put a pin in that. And let's modify our stuff.
It's a number?
What? No, let's modify the situation so that we can use that result. Let's replace this hoop with a circular sheet of charge. Okay? A circular sheet of charge. So I'm going to erase all this, okay?
No, wait.
Wait, I forgot to copy that down in the beginning.
Hold on.
I forgot to copy that down 3 hours ago.
Well, that's your bad.
Put that in our equation.
Too bad.
there.
Your equation holster? Yeah, put that in your equation holster. Okay, so now I'm going to have a circular sheet of charge. In the same, I'm going to orient it in the same way as before. So there's my x direction. That is the z direction, as the Brits say. Y direction.
Have you seen the video of that professor who draws the dotted lines like perfectly? And
Walter
super
Lewin
fast?
from MIT. Yeah.
It's like.
He has to use chalk though, so I remember like I watched the video.
Yeah, you have to use chalk. That's literally when I write a lot of the notes that I use to teach this class, I got them from those lectures. Those of you that struggle with this stuff and want to get a heads up this summer before you go to university, check out it's Physics 801 and Physics 802 from MIT. Walter Lewin, he's like the best physics professor in the world. And yeah, he can take a piece of chalk and just drag it across the board and it'll be a dotted line. And he can do it so it's just dots or it's dashes. He can like change the way that the dotted line looks just by the way he drags the chalk across the chalkboard.
He teaches at MIT.
Yeah. It's good stuff.
Chalk skills. We need this. What's your greatest accomplishment? Figuring out how to draw a dotted line with a piece of chalk.
All right, so we got point P here. Hopefully we can all agree that by symmetry the electric field is still going to be pointing in the x direction, right? And the gist, what we're going to do, we're going to consider this circular sheet of charge to be an infinite number of infinitely thin hoops of charge. So I'm going to draw my not a representative DQ. Well, it is representative DQ, but it's not going to be a representative DQ located on a segment of a hoop or segment of a linear part of a charge. It's going to be a representative DQ that's represented by a thin hoop. All right, so here's my thin hoop. That is not good. Not good, not good at all.
A thin almond.
Okay. Now I'm going to call the radius of that hoop little r, which is going to be confusing because we're going to have but bear with me. The radius of the large hoop is just capital R. What do you think the thickness of that little tiny hoop is going to be?
DR.
dr. D little r, right?
Yes.
Yeah. The width of that hoop is dr.
Doctor.
Doctor.
Is the width of the thing?
And doctor has charge dq located on it. So it doesn't matter how big the hoop is. If it's infinitesimally thin, it's got an infinitesimally small charge on it. Right? And that hoop, as we saw in the previous example, creates a charge or an electric field at point P that is purely in the x direction and creates the electric field dE. In the previous problem, we learned the total electric field due to a macroscopic hoop of charge is that equation there. But now dE is now that electric field is due to an infinitesimally thin hoop of charge, so it creates an electric field dE.
So
And
that
then if
would
I just
be-
what's that?
would that now be
Yeah, yeah. But instead of big Q there, it's going to be dQ, right?
Yeah. Oh, I understand
Sweet.
everything.
So everything.
Yeah, this is all physics.
Why are you so good?
So we're going to, again, use the result from the previous problem. And so we have that dE is just going to be kx dq. Put dq on the end because we're going to have to substitute over radius squared. Not big R squared.
Little r.
Here's little r squared. Plus x squared to the 3/2. Right?
Yep.
Now the issue here that's going to make this a little more difficult is dq.
We have to.
Because this isn't a representative segment on a length of charge. It's not a length. It's not charge per unit length. This is representing an areal extent, right? This infinitesimally thin hoop, I'm using this to determine the electric field due to an area of charge. Meaning that this hoop must represent an infinitesimally small area of charge on that areal charge. Does that make sense?
Yes.
Okay. So I don't define the charge density on dq as dq per unit length, charge per unit length, but rather charge per unit area. Okay? And that's our sigma. Sigma is charge per unit area, and so the macroscopic would just be total charge Q over over pi times big R squared, and the area density microscopic is going to be dq over, and I'll call it dA now, but I need an expression for that dA. And the easiest way, not most accurate way, but it actually comes out to be exactly as long as it's infinitesimally thin, I can snip dq and spread it out into a rectangle. Okay? Lay it out into a rectangle where the thickness of it is dr. And the length of it would be, let me be consistent here. That's dq. That's dr. And then the length is what? 2 pi times
R.
which one?
Big.
Little r. Now, if I take a circular hoop and cut it and lay it out, is it going to be a rectangle? No. However, the thinner it becomes, the closer it'll be to a rectangle.
Which is a rectangle.
And then once it's infinitesimally thin, then it will be indistinguishable from a rectangle. So this is fine. So dA then becomes what?
dr 2 pi r.
2 pi dr 2 pi 2 pi r dr. So it's going to be dq over 2 pi r 2 pi r dir.
So dq would then it be sigma 2 pi r dr.
dq is going to be, and usually we put the 2 pi first, but yeah, 2 pi sigma r dr. You might notice this is getting grosser, more grosser
Yes.
than the last one.
Order.
So, substituting all that in there, we get dE, the differential electric field due to the infinitesimally thin hoop of charge, dq, is going to be kx times 2 pi sigma r dr over little r squared plus x squared to the 3 halves. And I'm going to read, because I'm very meticulous about this. I am very error prone, as you might have noticed. And so I rewrite this one more time. dE is going to be, I'm going to bring the 2 pi out in front. 2 pi times k x sigma r dr over r squared plus x squared to the 3 halves. Oh boy.
And this is whenever I look at stuff like this and I go, wow, I'm wondering if I'll ever understand what's going on.
Remember, it just boils down to Coulomb's law. Just the force between two charges.
For some reason, this makes more sense than linear.
Well, you're a strange man.
Like, I understand this so much more than I did linear.
Cool. Well, it might be just that you're recognizing it more.
Finally, just
The more examples we do, the
put them.
okay. And then I integrate both sides. When I integrate the left side, integral of d just gives you total electric field. Yes, technically it's d in the x direction, but it's the only electric field. We determined that when we determined the electric field due to it, thin hoop of charge. And so that gives us the total electric field. What are my limits on this integral on the right?
0 to r, big R.
There at 0, big R. Mr. the Great is on fire today.
Makes sense.
So it's going to be the integral from 0 to r, because we're integrating the electric fields through these hoops from the little tiny hoop at the center and then adding up all the electric fields due to all the hoops that go out to the edge of the circular sheet. Okay? And what are constant here? Because I'm going to pull those out. Are you sure?
2 pi x.
2 pi, what about k? 2 pi k x sigma. That's it, right? We can't pull the denominator out because
Yeah.
we got an r there.
Correct.
R varies. If it varies, it's got to stay in the integral.
Yes.
And we're integrating with respect to dr, so if I see a r, it's got to stay there. And we can't break these two guys apart, so we got to leave them. So that'll be the integral from 0 to r of rdr.
Yes.
R d r.
rdr over r squared plus x squared to the 3 halves. Now you might look at that and say, hey, that looks similar to that other one. The other integral where we had dx over the square root of dx over x squared plus, I think it was y squared to the 3 halves power. So do I have to look that up in the table?
No.
Those of you in calculus AB might not know, but do we have to look that up in the table?
Probably not.
Those of you that are in BC or already know calculus? Or can you do that integral?
I just did the solution offhand.
I mean, I already know what the answer is, but
Yeah, but for us mortals, can you explain it to us? And we can do that integral. It's complicated. Real smart people. The person that I transferred from community college with and went to Cal with, I'm sure she'd be able to do that in her head because she's a genius. But I have to use U substitution.
Oh, yeah.
Right?
Okay.
We haven't learned that in BC yet.
What?
We haven't learned that in BC yet.
Oh no. All right. Well, let's talk about U substitution.
Yeah, okay, I remember this.
So the reason we couldn't use U substitution for the two of you that know you, the reason we couldn't do what we're about to do, the reason we couldn't do it in the if this was in this case, if this integral was in fact this, we gotta look it up in a table. We gotta look it up in a table. The presence of this r in front of the dr makes that integral doable. The reason is the chain rule. It boils down to the chain rule. That's why integration is harder than differentiation. Because to apply the chain rule, when you do a derivative, you apply the chain rule, right? You do the derivative of the outside, and then you multiply it by the derivative of what's inside, times the derivative of what's inside that, right? If you have parentheses and all that stuff, or other cosines and stuff like that. To go the opposite direction is much more difficult, because you have to recognize that within the integral, the chain rule is at play, and then you got to work backwards, okay? Notice I have an r squared in the denominator inside a bubble, inside a radical. But I have its derivative right there in the numerator. I have r in the numerator. If you see something like that, then you can use what's called U substitution. You will learn this. You won't need to know this in this class for this quest assignment, but to get to our result, we need to use it. So, we probably won't be able to finish this, so let me just briefly describe what U substitution is. And let me show it. Let me actually describe. Mrs. Fudge will teach you, and she'll be much more methodical about teaching you U substitution. Let me just show you U substitution in practice. U substitution. Why U? I don't know. Why not me? I don't know. U substitution.
I'm making you do this problem instead of me.
So you take what's in the bubble here, and you call it U. R squared plus x squared. Right? So anytime I see r squared plus x squared in my integral, I can just substitute U in its case, in its stead. And when we do a U substitution, we have to define U, and we also have to define du. And then we implicitly differentiate, right?
Yeah.
We differentiate both sides of this, du, and then we implicitly differentiate this side. Well, then we differentiate this side, in which case we get 2r times dr. You guys did implicit differentiation at this point, right?
Yes.
Okay. So we implicitly differentiate both sides of this equation. I think. Ms. Fudge, when she teaches you, if there's more to it than that, then she'll tell you.
Yeah, it looks perfect.
And then what's the derivative of x squared in this case?
0.
0.
Constant.
Very good. All right. So now I can solve this for dr. So dr is just going to be du over 2r. And now I have
Oh.
dr. And then I can plug in du over 2r for dr. Right?
Yeah.
Yeah, but then like the R's
Yeah,
cancel,
yeah,
so
yeah.
it's between-
Sorry. I haven't done this in a year, so.
Wait, you didn't get a slide here?
So I'm going to rewrite this. I'm going to rewrite this.
Hold on.
You said same.
Did you have anything to succeed last week?
Oh, yeah, so it's been a year. Okay, so 2 pi k x lambda. I'm going to leave out the limits here. I'm going to let Ms. Fudge teach you how to deal with the limits here. So I'm just going to leave out the limits of integration for momentarily so I can focus on the actual U substitution. Well, I know that dr in the numerator can be replaced by du over 2r. So I'll do that in a different color. So in the numerator, I have r. But then dr, let me write it like this. Numerator, I have r du over 2r is now in the denominator, right? Because I have du over 2r, right? And then r squared plus x squared is u, but u is to the third 3/2 power, right?
So R's cancel.
So r's cancel. Does that make sense? Those of you that don't know U substitution? I think I made that more complicated than it needs to be. If I have r dr in the numerator, I have r times du over 2r. Right? I'll do an extra step just to make it a little more clear. That's my numerator substituting this in for dr, using my u substitution. Divided by, well here, I've defined u to be r squared plus x squared, so that's u to the 3 halves.
Okay.
So over u to the 3 halves. So the electric field is then going to be 2 pi k x sigma times the integral of r du over 2r u to the 3 halves.
And then ours cancel.
And then the r's cancel,
And then you can.
and then we have an integral that we can do, right?
We have to make also pull out the 1/2 just to make it a little bit easier, and then the 2 cancel out.
Equals, oh yeah, the 2 is a constant, it can come out. I was gonna do that. So that's gonna be pi k
So it's 1/2 done.
x sigma times the integral, and it's in the denominator, so I like putting it in the numerator and flipping the sign of the exponent u to the negative 3 halves power du. Can we do that integral?
Yes, sir.
Yeah. We can do that integral. Hence the power of u substitution. The key, and I'm actually gonna stop here. We'll start by evaluating this integral from this point on Monday, Tuesday. Now, when you guys learn u substitution, you'll obviously get a lot more practice with this in your calculus class than you will in here. But understand the gist. To use u substitution, you have to recognize that there's a function, there's a piece of the function in the integral, and then you see its derivative somewhere else in the integral. Here we got r squared plus x squared to the 3 halves, and what's in that bubble, the derivative, is 2r. Well, I see an r in the numerator, so I can use u substitution. Again, Ms. Fudge will be much more explicit in teaching this concept. You're not going to have to use u substitution in this class and if you do so, it'll be towards the end of the class. But again, the result of this calculation is going to be very important for us in the future, so that's what we'll wrap it up with on Tuesday. All right?
Yeah, pretty much all of BC depends on u substitution after you learn it.
Does it?
Yeah.
Okay.
That's how